done today. So number one, I have all the pack back here. Let me show you because I did download all these reports and I'll put them together later today and post them and stuff, right? So I have all these CSVs from Packback that I'll put together for the week 10 stats so you can all see where you are. That's nice. The other thing I'd like to mention, I got a very nice email from a former student who took my IDS 201 course. Now, some of you may have heard of IDS 201. It's one of those that, most students consider it to be quite difficult. But on the other hand, it's also potentially useful. The problem, what makes it difficult is it's an intro programming course for Java. Java is a fairly complex language. But the good thing is, if you get competent at it, like this student, he said he had a few very nice job offers. He may have used the adjective sweet. Anyway, so he was very happy about that, and importantly, he was like, I didn't know what I was going to do with my IDS degree, but I'm really glad I didn't have to. Oh, he was really glad he didn't have to go to CS to do a CS major to do some coding. So anyway, that was nice, and it could happen to you. It's not super a plug for me or for IDS 201. I mean, if you are an IDS major, you probably ought to take IDS 201, but my point in bringing it up is that if you come in wanting to learn new stuff, things will usually work out well for you. So that's really where I'm going with that. Although it is always nice to hear from a student who says that I did something, that was useful in the real world. Okay. Anyway, our big thing, let me make sure I'm recording because we want to start recording. Am I recording? Oh, I am recording. Okay, great. We're going to do this, finish up the Google advertising lecture, and that will be that then. We would like to do it. I don't know why. I don't know what's going to, that was really weird. So, there you go, okay. All right, so Google advertising, we're going to start back at slide 18 where we left off. Okay, so we just finished talking about clicks, right, and how Google makes money off of, in most cases, off of clicks. But this brings up the question of distinguishing between good and bad clicks. So what Google wants is for everyone involved in Google's advertising system to be happy, okay? It wants the advertisers to be happy in the sense that when people click on their links, they're actually people, and they're people that are interested in the product and might possibly buy it. That's what the advertisers want, okay? Google wants the viewers to be happy. Google wants viewers to see ads that are relevant to their interests and that don't really interfere much with how long it takes for search results to be delivered, okay? And Google itself wants to be happy, and we all know what makes Google happy, right? Fat stacks of cash. So as long as Google's making bags and bags of money off of this, and everybody else is happy, everybody's happy. That's great, okay? But people get happy from good clicks. Good clicks mean an actual human seeing the ad saying, ooh, that looks interesting. I will click on this ad to learn more and possibly buy one, okay? That's what Google wants. Google doesn't want somebody creating bot traffic, phony synthetic traffic to click on ads for some reason. So let's talk about bad clicks. So some of you in this class who are shifty and devious may have already thought of some vulnerabilities in Google's ad model. For example, suppose you're an unemployed blogger and you want to buy pizza, right? But you write a shitty blog and nobody's visiting, and even those few people who do visit, they're not clicking on any ads, so you're not making pizza money. So what do? You start clicking on a few of those ads yourself. Aha, right? Second, competition. So suppose and Walmart are engaged in a mortal struggle that has finally come to the online venue, all right, the online arena. And Target has decided to sabotage Walmart. It creates a bunch of bots that scour the internet for Walmart ads. And every time it sees a Walmart ad, these bot programs, they generate a virtual click that Google treats as a real click and charges Walmart for, the click on the ad, even though since it's a bot, it's never going to lead to an actual purchase, okay? So those are some devious things, and Google has to be on the alert for that. So Google tries to distinguish between legitimate and illegitimate clicks based on the data it has available. So some of the simple things it looks at, Number one, the volume of traffic at the source, okay, or the destination. Number two, the time between clicks, right? Obviously, if you have some bot program that's generating clicks at an unsustainably high rate, Google's going to look at that and say, nope, red flag, not real, okay? And behavior on site. If your behavior on your site doesn't appear like a real human, Google may invalidate that click, okay? So what often happens, if you read about people who actually are using Google's AdSense. Remember, AdSense is the program where somebody not affiliated with Google lets Google run ads on their site. People who are doing AdSense, they're like, oh yeah, it was, my blog, blah, 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 and I thought I was going to make $1,000 from Google this month, but then they sent me a thing saying that half of my clicks were invalid, and I'm only going to make 500, right? You'll see people say stuff like this all the time. So Google has an initial first pass of how many clicks you get, but then it looks at all that and says, yeah, you know what, a lot of these probably aren't real. So we'll talk about this. All right. So imagine that you are a very hungry, unemployed blogger. I hope that never happens to any of you, by the way. A very hungry, unemployed blogger looking to score some pizza dollars via Google. Okay? This is your plan. Now, your first pass through, your first attempt, you visit your site repeatedly throughout the day, right? I would say you visit your home page, not just the whole site, but your home page. There we go. Repeatedly throughout the day, and click on an ad and reload. Okay, so you do that. At the end of the day, you have generated thousands of ad clicks. Will Google pay you? I ask, will Google pay? I mean, we know they shouldn't, but why not? Why wouldn't Google pay you? How will they recognize that this is phony, bogus-ass traffic? What's that? That's certainly one thing they could do. They could say, hey, why is this one person from this one IP address visiting the same site like 5,000 times during the course of a day? That's ridiculous, right? Nobody does that, right? So again, excessive traffic from a single source, right? What else? That's one thing. That would be enough right there. But what else might Google look at? What are some red flags? If you were a human, yeah.
Well, you can look at like you get data like how many active compared with how many are being shut down.
Okay. Yeah, you might look in various ways. I mean, of course, you're always going to compare to prior data in some sense. But one thing you might look at is people don't just go to the home page, right? People don't go to the home page and bounce away and reload and do that all day. That would be very unusual behavior, right? What else? The click-through rate is going to be absurdly high, right? Here, basically, the click-through rate is going to be 100% or close to it. Typical click-through rates, 1%, maybe 2%, right? Maybe 3% if Google's doing a really good job of matching terms with search results, right? But AdSense usually isn't that good. So I'd say like 1% or 2% would be great. But here, right, it's going to be like 100%. There's one ad on the page, blogger keeps on clicking it every visit. Google's going to say, nope, no way, not real. Okay? So stuff like that. Now, let's go. Okay, so that fails. That fails, so you try again. And this time, you go to a few different places throughout the day, right? Like you get on the Starbucks Wi-Fi and the McDonald's Wi-Fi and the UIC Wi-Fi, aside from your own home, and visit your site and click around a bit, and then click on ads. Will this work? Will Google pay you? What do you think? I'm guessing probably not. I'm guessing this is slightly more sophisticated, but it's not terribly sophisticated, right? Number one, even though it's a few different IP addresses, remember, the percent, click, right, the click through, the CTR, is still only a few percent. And this will still be very high, right? You click around a little bit. Importantly, every visit seems to lead to a click, right? I mean, how often does it happen for any of you that you go to a website and you click on an ad? It's unusual, right? Whenever you go to a website, sure, you might click on an ad once in a while, but the idea that 100% of website visits are actually going to lead to an ad click? Also, I might add, none of these clicks will lead to actual purchases, or probably any sort of conversion, non-purchase ones. Okay, so with Google's web analytics data, they can look and see, hey, what is this person actually doing on the website? And a normal person who's interested in a product will click on the ad, like learn a little bit about it, like scroll up and down on the page, read some stuff, maybe click on a few image thumbnails, and once in a while actually buy it, right? But if Google has a batch of data like this, it's still only from a few IP addresses, it's still behaving in a non-very human way, and it's repeatedly going to the site to do ads. Probably not, right? Probably not. So let's add that. Now, last thing. Suppose you now have acquired a botnet. Anybody know what a botnet is? It sounds scary, doesn't it? Nobody knows what a botnet is? They've been in the news a fair amount in the last 10 years. A botnet is a bunch of machines that you control, right? You don't own them, but you have some malware running on them so you can make them take arbitrary actions on your behalf. Botnets are commonly used in distributed denial of service attacks, where you try to shut down somebody else's network. Yeah. Anyway, suppose you have a botnet, right? And it has a botnet of 1 million machines, okay? And you decide that you're going to be a little bit more sophisticated. And you decide to have many thousands of bots visit your site and browse around, because you can have them do that. You can write scripts where they do that. And a few of those bots will actually click on ads. Okay? On any, and X will change every day. Will this work? You think that might work? I'm going to tell you there's a pretty good chance that this works. Reason is, Google can't filter out every phony thing, right? If there's a small number of actions and it seems pretty random as far as Google's concerned, the only thing that might tip off Google is if your website traffic has suddenly spiked, right? But if you're already getting a fair amount of traffic and you add like a couple thousand more, and out of those couple thousand more, you add a few more ad clicks, it's not going to throw a major red flag at Google. And the thing is this, getting a botnet like that is not a trivial thing, right? So it's like, suppose you design a new flamethrower, right? A new military grade flamethrower, and with that, you could sell it to the Department of Defense for millions of dollars, right? You say, hey, I got this great new design, right? It's a flamethrower that doesn't blow up when somebody shoots at it. Oh, cool. But instead of doing that, instead of cashing in big like you could with this botnet, you could do any sort of like ransomware attacks, or you could do denial of service threats. There's a variety of ways where you could make money with botnets that would be like way bigger than this. This is the equivalent of you designed that flamethrower, and instead of selling the design rights to the to the DoD, you decide that you're just going to go roast fire ant hills in South Texas. Okay, because why? Because right? It's overkill. So this sort of thing, Google's, even though, yeah, it would probably work, Google's not super worried about this because somebody with a botnet is not going to chase these kind of trivial small potatoes. Okay? All right, so again, in general, Google's not going to detect every possible thing that might be a phony click because it's not going to have that data. But the obvious red flag ones, it's going to catch those. And the ones that are like borderline cases, well, you need a fairly sophisticated setup, but you'd be basically chasing pennies with that to do it. Okay? In most cases, it's not going to be worth the trouble. All right. I hope that all made sense. Okay. Now, next thing, ads as objects. So in a variety of ways, we've talked about what objects are. They're things that hold data and can do actions. And objects in this sense, we're talking about ads and how the ad data is structured to display properly on a web page. So if you have ever looked at a product on Amazon, and then within an hour or so, you start seeing ads for it online, right? You go to some other site and there's ads for it in the margin, and you're like, what the hell? I just looked at those pillowcases on Amazon and now they're, how do they know? Right? Well, the way they know, just like Google has AdSense, Amazon has its own ad system where people can join up and Amazon will run ads on their pages. And the way Amazon gets the data for this is basically Amazon stores it in a little data file on your machine called a cookie. It stores some information about what products you may have looked at, things you've added to your cart, stuff like that. And when a web page comes up that's running Amazon ads, then Amazon grants it permission in a sense to look at that cookie. Actually, Amazon does it through the web page itself. Amazon looks at that cookie and grabs the content necessary to, you know, hopefully attract you to buy something that you looked at before. So here I'm going to draw a picture, and I hope this will make sense. So imagine you here, you are the client or the user, that's you, okay? And then we have a web page, and then we have Amazon. And I'm going to draw some boxes. Here's the web page, and here's Amazon. Close enough. Okay, and in the web page, there's a box here that Amazon uses to run the ads. Okay, so we'll just say ads. Now, you request the web page, right? So you visit the web page, ta-da! When the web page is being constructed, one of the things that gets constructed is it has to put in content for the ad. So the ad will request to Amazon, we'll say, give me ad, please, okay? And then, we don't have to get into the details, but Amazon database magic produces the relevant ad, okay? And what does the web page have to send? Well, obviously, it will have to send, must send the user ID, right? However that's clarified. If Amazon's going to show you products that you just looked at, it needs to know who you are, right? So it's got to send you that. And that information would be in the cookie. That's fine. It could have it. And other things it might send is like hardware, OS, browser, right? So for example, if Amazon wants to display an ad that will display well on your machine, considering your combination of, you know, hardware and software, it might want to know that information, like whether it's a mobile device or a big screen, what the screen size is, what the you know, color capabilities are, all that kind of stuff. Amazon might want to know that as well. Okay, so when Amazon gets that information, it can respond back and say, here is ad you asked for, right? You requested. Ta-da, and there it happens. Okay, now, we understand this process, I hope. Any questions about this part? Would anyone like to know more? Yeah, okay.
So if you're like any of us, we're on like some random web page and we accidentally click on an ad, does that generate revenue for the owner of the site?
Short answer is it depends. All right, one of the things that Amazon, that any of these ad services do, and Amazon tries to only treat real clicks for the same reason Google does, right? If you accidentally click on an ad and immediately bounce back from it, that's usually like considered a red flag that you clicked accidentally and it's not going to count. Okay? There was a window a few years back where quite often sites would run ads at the top of the page, and when you went to like close it out or go back or something, you know, the ad would jump a little bit and it would automatically be under your cursor and you'd like catch it. But yeah, Google started basically, you know, other ad services too started excluding pages like that because, you know, it was bogus. And yeah, so they're pretty good at determining real clicks versus fake ones. Yeah.
Like a follow-up question. So companies, like if they're trying to advertise something through Google, they have to pay Google, right?
In most cases, they don't have to pay Google up front.
That's because, like, with one of my dad's businesses, he's like never took on ads on Google because it charges us a certain amount of money.
Oh, yeah, for sure. Like, for example, suppose you're ordering pizza, right? And you go to Google and you do pizza delivery. If you click on this ad, that's probably going to cost them $1 or $2, versus if you scroll down a little bit and click one of these, right? One of these other links. So yeah, even if you do like Pizza Hut, there's a good chance there'll be an ad right at the top. Yeah. So funny thing, and the reason why, and you might add, this is like outside the scope of the course, but I'll tell you, this is one of the things I talk about in web analytics. The reason why companies sometimes do this, because number one, they know you're looking for Pizza Hut. They don't know with 100% certitude. I mean, Pizza Hut's pretty sure it's going to be at the top of the screen, right? But it doesn't know with certitude that Pizza Hut delivery is going to be at the top of the screen. It could be something about, you know, Pizza Hut as a business, Pizza Hut new in the news, right? They want to make sure that this is absolutely the top thing you see. The other thing, competitors can bid against Pizza Hut, right? There could be like Domino's could be actually bidding on the search terms for Pizza Hut, so its ads rank high. And then when you try to order Pizza Hut, you'll see an ad for Domino's at the top, and Domino's can poach Pizza Hut customers. Like if you do this for Amazon Web Services, we'll do Amazon Web Services migration, we'll see other businesses there, right? So here, DB, this is one that like helps you send your stuff to Amazon. On occasion, you see like Azure as, they're not doing it now. Microsoft Azure, another competing cloud service, they used to run ads against Amazon. Let's see if we do Azure migration. See who's running there. No, Azure is right at the top of their own. So they want to make sure that Amazon doesn't come in and poach anybody, or that all of these other ads for people that'll help you migrate your stuff to Azure, they want to make sure that they're at the top of the list. And they must think it's worthwhile. So, right, because you got to figure Microsoft more or less knows what it's doing. That should be a default assumption for any reasonably successful business is, you know, they may not get everything perfect, but by default you should assume, yeah, they're probably making reasonably good decisions and they know what they're doing. Okay. Is that good? This has been a good, yeah, okay. All right, 2 thumbs up. All right. Okay, so from this, right, going back to our image about Amazon and the web page, so the inputs, basically that user history, right? Who the user is, what they've looked at, and that's data that Amazon can pull from the cookie. You also need actions for that web object, for that ad. Primarily, what happens if somebody clicks on it, right? Basically, where does it link to? How is that data tracked? Because you know Amazon wants to track who's clicking on the ads. And then finally, any outputs, right? So response or non-response. So for example, Amazon might say, obviously they're going to track if somebody clicked on it. They might also track if it stayed on the page for a while, somebody was at the page and they totally ignored it for a long time. Or they might even track like how long it took for somebody to click it, right? And yeah, stuff like that. Any other output they want to send along. So there you go. Now, how this relates to APIs, application programming interfaces. Remember, APIs, we've mentioned them before, APIs are interfaces between applications. So the applications expect to receive information in a certain format so they can process it correctly. So, for example, in our paint bit here, in order for this Amazon Magical Database application to process the request correctly, it needs to have the user ID, right? For sure it needs the user ID, and it can also accept some of these other parameters like hardware, operating system, browser, that could help Amazon make better decisions about what ad to show. Likewise, Amazon is going to display the ad in a certain way, right? There's a certain standard procedure it goes through. It delivers some ad to this, and the ad presumably will have an image, will have a link to somewhere, will have a mention of a destination where any relevant analytics is going to be sent, like if someone clicked on it, what system in Amazon gets notified, okay? So that's what we mean. So there's standard format for input, standard format for outputs. Ta-da. And that's how it works. Okay. The nice thing about this allows you to design generic objects that conform to standards. Very important thing, the designers don't need to know the machine-specific details, right? So it can help, but they don't absolutely need to. Amazon can just say, yeah, you know what, you tell me what user it is, I can give you the history of what they're looking at, right? Or I can give you an image. Now, in the case of this sort of stuff, sure, knowing the screen size is probably going to help. You're going to display an appropriately sized ad. But strictly speaking, you don't absolutely need to know that, right? It can help though. But you certainly, you know, again, don't really need to know the operating system or the browser in order to get this information. Might be useful, but in a lot of cases you don't. So just think in general, if you have your browser and you are contacting some web server, that's kind of an API right there. You tell the web server the page you want to look at, and the web server is going to send you all the HTML content of that page. That's the standard object they're sending you, this long document, and your browser is going to display it in accordance with the normal rules of HTML, right? The web server doesn't really need to know what kind of hardware or operating system you're running, right? But again, with the caveat that some pages run better on some browsers than others, but web server doesn't really need to know. All right. So that's what APIs are useful, and we'll have more to say about them in YouTube. So again, as far as any object generically, the formatting essentials for an API, you need some description of the object itself, which includes the data it holds and the actions it can do, and then the formats for all of those, right? So basically a list of here's the data, here's the actions, and here's the format. Here's how those lists are going to be structured. Right, so maybe the user ID first, and if it's sending along some hardware model, some operating system, some browser, it has codes for all of those. And all that information, remember when we were talking about JSON and XML back in the day? So same thing, you can use those as object description languages to describe, for example, what's contained in an ad. And XML is around, it can be used, but like we said, XML is in many cases not widely used anymore. JSON is better for a lot of purposes. It automatically converts to scripts on web pages, but yeah, conceivably you could use either. Okay. And that's it. That's all about what I have to say about advertising and APIs and stuff. So the rest of this, we're going to talk about Google's databases, and then we're going to talk about some implementation issues with them. So Google is really big, and not surprising, they have massive, massive databases for a lot of different systems, right? So advertisements is one, all the analytics about how users are responding to ads and how ads are performing in conjunction with various search results, cached web pages, all the web analytics data that they might be grabbing from websites that are running Google Analytics, and lots more, right? So Google has lots of data. This is no surprise. But what might be a surprise is that Google's advertising system runs on an extended SQL system that Google calls NewSQL. So it's not the same as NoSQL because it's basically a relational database setup, but it's NewSQL because it has some functions to basically run a little smarter and arrange data more efficiently so you can pull it faster out of the system, do faster updates. So the base system for Google is called Spanner, and Spanner is this monstrously large system that spans the entire operation of Google, and there's a lot of other systems built on top of it. The database system that's on top of Spanner holding the ads is actually called F1, and we're going to talk a little bit about that. Okay, so F1 is a very, very, very big relational database management system. So just think relational database, okay? And surprisingly though, like NoSQL databases, it's scalable to run on many, many instances of standard hardware. So Google's not buying special, customized, super high-end, cutting-edge hardware to run this. It's buying very ordinary commodity servers, the same kind that any other business uses. And if anything, it probably tends to go a little bit cheap on them. It just has a lot of them running in parallel. Okay? The operational properties of F1. So think about this for a second. Just like loading a picture to Facebook doesn't need to be super fast. What needs to be super fast is retrieving the picture. Same thing for ads. Doesn't really matter that much if you shave off a few milliseconds off the upload time for an ad. What matters is that the ads can be retrieved fast enough from Google's system that they don't slow down the search results too much, right? Because that's what Google really cares about. And the important thing, again, every ad gets uploaded once, but might be pulled from the database thousands or millions of times. So again, the write speed in the system doesn't matter that much. If it takes a second or a minute, whatever, you only have to upload it once, right? What matters is that pulling it out of the database is super fast, okay? The second thing, ads are going to be stored in a standard format, which is what you would expect in a relational database, right? This is basically F1 is basically a relational database. But what did we talk about earlier? We talked about how a lot of times images don't store well in relational databases, right? Anybody remember that? What is the problem with storing images in relational databases? Yeah.
Different images can be different sizes.
Yeah, and why is that a problem?
Because with relational databases, you have like a standard amount of space in each cell.
Yeah, right? So if you have a relational database, one of the things that's built around is the idea that for any record, a field will have the same size, right? So if you have varying image sizes, some are very large, some are very small, you're going to waste a lot of space in your database, in your storage media, because you're going to have to allow for room for the biggest image you can have, right? So how does Google get around this? How does Google manage to store these images in a relational database? Well, let me make it very simple. If the problem is that images can have variable size, then the solution must be to have all the images be the same size. There you go, right? So Google can say, look, you want to send us an image? Great. It's got to fit these criteria, right? It's got to be, such and such height, such and such width, such and such pixels, right? And they could potentially have different database tables storing images in different sizes, or they could upload one very high resolution image and then shrink it down or reformat it as necessary to appear on a particular web page. We don't have a lot of detail around that, but it doesn't really matter. What we know is to make this whole relational database setup work, in some sense, all the images in a table have to be the same size. Does that make sense? I hope it does. Okay. Anyway, if you want to do some extra reading, there's a lot of links throughout this if you're interested in this stuff. Okay. Second, Google Spanner, right? So we talked about F1 and its properties. Second thing, Spanner, right? Spanner, again, system that uses SQL but approaches NoSQL performance levels, which is kind of magical. We'll talk about that in a moment. But the big thing is, even though it's a really, 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 really big system, it pretty much follows ACID properties. Okay, and one of the things we talked about with ACID properties was that if you have a very large system, following ACID properties tends to slow it down a great deal, which is usually bad. Okay, so ACID properties, yes, they ensure that data integrity is there, but for a very large system, in various ways, they're going to slow it down maybe too much to be workable. That's why Facebook has an eventual consistency plan for doing, updates and notifications to users. That's why Google has an eventual consistency plan for when it updates, its page rank formulas or, updates pages that it has stored in its index. Okay, we'll talk about that though. But second, as a cloud tool, businesses can migrate their stuff there without having to change the code, right? So the reason why Spanner specifically uses SQL is Spanner is a system that is used not only by Google, but also the base of their various cloud systems that they're selling as services to their business clients. So if everything were written in some fancy new kind of structured query language, what would happen is this. A business would say, hey, Google, we want to run our stuff on your cloud. And Google would say, well, that's great, but here's the thing. We use this very different, kind of database language, and you're going to have to update all your code to work with that. And the business is going to be like, well, but that's a lot of work, and it's going to take a lot of time and cost a lot of money because, database guys aren't cheap. And Google's like, well, yeah, but, this is the language we're using. And the business is going to be like, well, we're going to go see what Amazon's got, right? Google doesn't want that. So what do? They say, yes, our system is fully SQL compatible. If your system is set up on SQL, you can bring it in. You don't have to change any of the code. You can just start running it right out of the box, and it'll be great. But if you need it, we support these new SQL statements if you want to optimize some stuff. And we use some of that stuff to optimize our own things. It's there as a potential option. Okay, and businesses will be like, yeah, okay, that sounds great. So let's talk about how they do it, though. So here's a chart or a picture. Everyone likes pictures. So on the y-axis, we have consistency, right? And that basically means following ACID properties. On the x-axis, we have speed and flexibility, the ability to do tasks quickly and to the ability to make database changes, right? So traditional database, as long as it's not too big, right? It says great for moderate size, and as long as your database schema doesn't change frequently, right? So your schema is basically the setup of your database, what tables you have, what fields are in which tables, things like that. For a large relational database, changing the schema is a huge pain because you have this very large, carefully calibrated system with data located in certain places and distributed over multiple machines in a way that you can run these queries efficiently. And if you make a small change to the schema, like you add a new field or even resize a field, you kind of have to go through that whole careful calibration process all over again, possibly add in extra hardware. It's going to be a big headache, right? So you really don't want to do that. On the other hand, NoSQL systems, while it is possible to design a NoSQL system that completely follows ACID properties, in most cases, NoSQL systems, they're going to cut some corner that a relational database follows, right? Whether it's in terms of ACID properties or other things, they're going to cut some corners, and a typical thing, again, is eventual consistency. If there is a situation where a system doesn't have to be perfect all the time, then yeah, you can let that go in favor of speed. Likewise, NoSQL systems, because they often don't impose a particular structure, like we talked about key value stores, it's very easy and painless to make those changes, right? What you give up is the ability to run certain kinds of queries across tables quickly, but you can very easily change the database, right? There's no free lunch, so you give up something to get something. Now with Spanner's there kind of in, you might say the best of both worlds, or that's what it's trying to be. It still has very, very strong consistency guarantees. Part of the reason why Spanner has very strong consistency guarantees is that it's being used by a lot of different clients at the same time, right? So remember when we talked about Amazon transaction processing, we said Amazon can process several hundred transactions per second on its own, but its system for all of its various business clients can process 1 million or more transactions per second. And the reason why that's manageable with ACID properties is all of those operations are not accessing the same database, right? Every business client has their own separate database. You only need to maintain ACID properties within one. So there's not going to be that interference across them. It's like you have 1,000 different database systems running on entirely different hardware. They're not going to interfere with each other, right? So Spanner can, in general, provide really good consistency guarantees. And even when a system is large, a lot of that's going to happen, they can push into RAM because it's Google and they have those resources. On the other hand, Spanner is very changeable, right? Because it's built for change. Number one, Google's constantly growing. So this idea that they're constantly revising their algorithm, updating it, rolling over data from one place to another, recalibrating their systems, they're kind of constantly doing that anyway. So a schema change to a database, especially one that's only a small part of Spanner, is not going to be a major problem for them. It's kind of already built into their running model. So That's what Spanner does. It tries to provide a good mix of strong consistency guarantees as well as speed and flexibility comparable to NoSQL systems. It's not going to be as fast as a NoSQL system that's purely designed for that, and it's not going to be as immediately consistent as perhaps a traditional relational database, but it might be good enough for most the vast majority of purposes. Okay. Now one more, BigQuery. BigQuery is the next system we're introduced. So the short version of what BigQuery is, it is a system allowing fast queries involving very large tables. And when I say very large, I mean hundreds of millions or more records per table. So let's contemplate this a bit for Amazon, not for Amazon, for Microsoft Access. And you can see the problem. Suppose you have a record, a table that is very large and has 10 billion records. And before you say, hey, why would a table ever have 10 billion records? I'll tell you why. So Google Analytics, we've talked about, the web analytics platform Google provides, has a premium option called Google Analytics 360 that can handle up to 20 billion website hits per month, right? So for everyone who visits your website, they can pile up that data up to 20 billion records per month. That's a very large database table. Now, you try to store that on a regular machine, right? Suppose you have like 10 billion records, and you want to store that on a conventional nice machine. Let's say it's 64 gigs of RAM, right? It's a good machine. But what's going to happen? Just the ID number for each record, that if the key field is a unique number, that's going to have to be 8 bytes. That's standard data type, a long integer. Once you get above 4 billion, you have to use 64 bits to hold that stuff. 10 billion records times 8 bytes per record, 80 billion bytes just to hold the record IDs, right? You try to run that in Access, forget about the speed problems. Your machine just simply doesn't have the memory to even track the ID numbers of the records all by itself. If you have this kind of very big system, right, this kind of very big data batches, you need a highly specialized system that can handle that kind of scale, okay? So that's, again, a little bit beyond the scope of the course, but I hope gives you some understanding that, yeah, ordinary machines can't handle batches of data that big. So Google provides that. And again, if you're using Google's premium analytics service and you're getting that much data, it's not much good to have that data unless you can run queries on it. So Google says, you know what, you're shelling out for our premium analytics. We're also going to provide you the necessary tools to run queries on it so you can learn from your analytics data. So BigQuery is a very special, very useful specialized system for the right problem. For businesses using something like BigQuery, obviously going to be vastly cheaper and faster than designing it themselves, if they even have the capabilities to design it themselves. All right. Now, this part here, this is definitely beyond the scope of what I'll ask you about on exams, but this is something it's good for understanding. So, relational databases, the whole point of relational databases is you can run queries involving multiple tables, right? And involving multiple tables in a query is what's called a join operation. You join data from 2 tables together. But there's certain kinds of joins that involve essentially multiplying tables together. And if anybody remembers from Access, you remember when you were setting your relationships, there's a little checkbox that said enforce referential integrity. Yeah, I see some nods. Yeah, what that does is it basically checks to see if you include a field that exists in a value that exists in another table as like a foreign key, you check in there and make sure that it actually exists in that other table, okay? Otherwise, you won't be able to create that new record. That's what referential integrity is. Now, even if all your tables had referential integrity when you entered in new records, every now and then you might want to go through and cross-check to make sure that nothing has gone wrong in any of the databases, right? That none of the data has been corrupted somehow. And in order to do that, you need to do this operation called an outer join, where for every value in one row, you check it against the entire contents of every other row in the other table, right? And that's essentially multiplying the tables together. So, multiplying large tables together is a tremendously huge operation. If you had an infinite pool of RAM, you could just bring it all into RAM and run the thing very fast. But in practice, machines don't have an infinite pool of RAM. So what they have to do is load a batch of data from disk into RAM, run the subquery on it, load in another batch of data from disk, run that subquery on it. And that's a lot slower, right? Because you're accessing the disk drive instead of just having it all there at RAM speed. The other, if that table is so large that it's actually stored on multiple machines, then guess what? Now all of a sudden you're not even talking about running this on the same machine. You're talking about adding the disk drive delay to the network speed delay, and that's going to be super slow, right? So what often happens, real businesses, they say, yeah, we used to have these queries. It could take days. It could take a week to actually run. But then we went to BigQuery, and it got done in 30 seconds, right? Last I checked, any query that runs on BigQuery has to be completed in 30 seconds, or else you'll get some failure message. You're like, what the hell are you trying to do? You tried to run a query so big, BigQuery couldn't run it fast enough. You have to break it into smaller queries to actually try to run it. Okay? So one of some tricks that Google has to basically run these kind of things faster. Number one, I'll just give one. Imagine if you have a very large table with 1 billion records, right? Too big to run on a single machine. And you want to do a table join with another much smaller table, right? And that much smaller table maybe only has 10,000 records. So what could happen? What could happen is that Google slices that 1 billion record table into 100 or 1,000 different segments. Each of those run on one machine, but then Google copies the entire smaller table to every machine, right? Because at that point, versus 1 million records, 10,000 is like a rounding error. And so then you have all of these subqueries executing locally on their machine. You get around the network connection speed problem. So tricks like that are what Google does to make this BigQuery stuff run faster. But again, if you're wondering about the why behind this, there's a little bit of the why. How does Google actually make this BigQuery stuff run faster in a way that ordinary businesses can't? Tricks like that. Okay. And this is basically that same kind of stuff here, right? So you might have the case where one table is very large, very, very large, the other one is small, right? And there's another case where if both tables are large, there's ways to manage that as well, to decompose that into groups of queries. Now again, eventually you can overload BigQuery. Things can get too big, but if you're interested in this stuff, I should mention, I think, Stack Overflow is your friend, right? That's one of the things I often say in 201 and 313. If you have a question about technology, especially about coding, Stack Overflow is your friend. There's a very good chance that someone in the last 15 years has wondered the same thing as you and posted the question, and there's probably a lot of very good answers posted up there. So if you want to learn about stuff like, how databases get overloaded by these operations, again, Stack Overflow is your friend. Okay. Now, here we are. We've talked about BigQuery. We've talked about Spanner. They probably both sound kind of similar, right? BigQuery can process a lot of data very quickly, but so can Spanner. So probably many of you are asking right now, so what's the difference? Well, I'm very glad you all asked, because here's the answer. Spanner is good for a lot of small operations that happen quickly, right? So things like transactions. If you have a lot of different transactions that have to be processed quickly, Spanner's great for that. It's comparable to Amazon's EC2 system, right? For application hosting, transaction processing, stuff like that. Think of Spanner as basically like being a bigger version of EC2. BigQuery is a lot like Amazon's S3, right? Amazon's S3, every business can get a data blob, basically, a key value store. They have their own separate large pool of data, and they can run analytics on it. That's basically what you're doing with BigQuery, right? I mean, the details are a little different, but BigQuery, you have a bunch of data, you can send it to BigQuery, you can get the results back pretty quickly, right? Same kind of idea. So BigQuery you use for relatively infrequent but really massive database operations. That is the right tool for that job. Okay, we'll talk about an implementation, but before we do, we got to go through some terms and definitions, and I apologize in advance for that. Okay, so terms and definitions. Number one, a data warehouse. I like this term, data warehouse. It makes sense. Everybody knows what a warehouse is, big building you store your stuff in. So a data warehouse holds all the data belonging to an organization, okay? Second term, data mart. I never liked the term data mart, but you know, this is something that exists outside of me. So data mart, the idea is all the data belonging to one functional area. And I guess the logic for calling it a data mart is getting data from that is kind of like a purchase. You have to go to that department and ask them if you can buy this, and if they say yes, then they give you the stuff. I guess that's the logic. Okay, so a data mart is part of a data warehouse and typically owned, operated, controlled by a specific functional area like accounting or finance or operations, whatever. Now, remember, we talked about the natural growth process for most businesses. They start out small with different departments having their own separate pools of data. Over time, these databases get big. It may create problems, right? We talked about database silos. Now, if you're trying to combine data in one storage system, that's easy. That's like throwing a whole bunch of your shit in your garage as tight as it'll fit. It doesn't really create a problem, right? Storage is cheap. When you talk about a 1 terabyte hard drive costing like $40, that's nothing, right? If you're a business that can generate that much data, spending a few hundred or a few thousand dollars on storage media is trivial, right? It's just not really a thing. However, the problem is when you have to access that data quickly. So what it used to happen 30 years ago, suppose you wanted to make a purchase, right? You're a business and you say, well, it's December, December's coming up, we need to have 1,000 bikes on our floor by December 1st, so we're ready for the Christmas rush. And so in order to get that, you call Susie over at Schwinn. You say, hey, Susie, this is Woolworths here. Can we get 1,000 bikes by December 1st? And Susie, she doesn't have that information right away. She's got to talk to operations and see if even building 1,000 bikes is feasible. She's got to talk to accounting and see what the status of your account is. Are you over on stuff? Then once she gets that information from accounting, she's got to talk to finance and figure out what credit terms she can offer you, right? She may need to talk to the suppliers to operations to find out, hey, maybe we only have 500 bikes on hand. Can we get the components in order to build that extra 500 by December 1st, right? So there's a lot of questions Susie needed to ask to get that information back. And what would happen 30 years ago is you'd place that call and Susie would say, okay, yeah, let me see. I'll get back to you in 3 to 5 business days, right? But internet now, nobody wants to wait that long, right? It becomes a competitive advantage to have that information available quickly because Woolworths is going to say, oh, sorry, Susie, you know what? If Schwinn has taken 5 days, we're just going to go and we're going to talk to some other guys and we'll see if they can get the bikes. And they'll get us the answer right away, right? We know it, fine. Okay, so all these businesses, what they needed to do is integrate all those separate databases together so that people could access the data they needed to in an appropriate permission-based way. And it was a difficult thing, right? It was one of the big IT trends for the 90s and the aughts was creating these kind of common systems to bring all of these different, separate, disparate database systems together. And that was ERP, which again, we've mentioned ERP before, but that's what ERP is. You take all this data from a business and integrate it into one common system, right? And it's a big deal. You can look up I looked up there were a lot of failure articles from the 90s. The one I happened to find in my morning class was one for Hershey's, which I think dropped $100 million on an ERP implementation that didn't quite work out. I remember other ones. It was a research paper, not a published thing, but thing I did for a class my first year of grad school. Wrote this long thing about different implementations for interoperability for ERP and found all these different cases where businesses dropped like 300 million on it and like at the end had nothing to show for it. So anyway, but when it went well, in essence, you got rid of Susie, right? You got rid of Susie, you didn't need her anymore. You could just go to the website and say, hey, I want to know if Woolworths can get 1,000 bikes by December 1st, and the system could actually correctly access all the information it needed to find out if that was possible. Now these days, practically all large businesses have an ERP system, right? The ones that weren't able to successfully implement it have gone by the wayside. And a lot of medium and some small businesses do, because the costs of ERP have gone way down. And on top of that, those smaller and medium businesses, they don't have as much data to manage. The process of integrating everything isn't quite as painful. Now, the case we talked about back in the Amazon thing was about a large multinational oil drilling operation. And you can imagine that realigning all the different separate national level databases that are all encoded in their own local language with local terms, making all of those a perfect apples to apples comparison is not a trivial thing, right? They have a lot of different database tables, and for every one of them, you have to convert it to some standard. So you have to define what the standard is and then do the conversion for each one. But once you've done it, then it's done, and the system tends to work great. Now, I will mention a little bit of historical detail, so we have a bit of time for that. So this is something they used to cover in IDS 355. They probably don't anymore, but a little bit of the history. So MRP, again, outside the scope of the course, I'm not going to ask you about MRP, was materials requirements planning, okay? And what this was is basically asking if the business has enough resources to fulfill an order, right? So, for example, enough labor, enough components, and free system capacity, right? And this is something you do. So if you place an order for 1,000 bicycles, the business could say, well, we have 500 bicycles on hand, and we have this much space available in our production queue over the next few weeks, and our suppliers are supposed to bring in this many things, and we have this many components on hand. They can tell you whether they can fulfill that 1,000 bike order or not, right? So that's what MRP was doing. It's basically saying, do we have enough stuff on hand to fulfill orders? Well, the next step, MRP2, was basically MRP plus transactions. Okay, so they handled all of those transactions, getting stuff paid for, right? So they integrated finance and accounting with it as well. And then finally, ERP was MRP2 plus everything else. Okay, and so ERP didn't just happen out of nothing, right? There was a trend over years where in the 70s, 80s, companies were building MRP systems. Then eventually it shifted to MRP2 because they're like, hey, wouldn't it be handy to be able to handle transactions in the same system? And then finally, the internet made it very clear that, gosh, we need to have everything in our business linked to a single database system. Okay. So that's a little bit of the historical progression there. Now, we're going to look at a specific case for supply chain management. So, supply chain management is the business function associated with getting stuff where it needs on time, tracking where it is in progress, and handling all the transactions around that, and gathering analytics data so you can improve delivery processes down the road. Okay? Supply chain management does all that stuff. There's lots of good careers in it. We have some 400-level courses in it in the IDS department. It's a thing. Now, as a business function, supply chain management requires inputs from a lot of different areas, right? Number one, marketing. Marketing can tell you, hey, what's the forecast for demand for this product, right? And how is that changing? What's the trend? Is it going up? Is it stable? Is it going down? And marketing can do that for the entire set of products you provide, so you can have an idea of how much capacity you're going to need as far as deliveries. Number two, accounting. Managing those billings, right? So accounts payable, accounts receivable, accounting's going to have to track all of that. And operations, where the work actually happens. So basic questions, what capacity is available now to fulfill new orders? Because supply chain management isn't just stuff going out, it's also arranging for shipments to come in, right? In some cases, the business may actually deliver the inputs to itself, right? It partners with another business, says, we're going to go pick them up and deliver them back to ourselves. Okay. Anyway, if you have an ERP system that has high database consistency, right, it basically, the answers are always there, you're going to get very fast, very correct supply chain management decisions. So if somebody wants to find out, hey, where is my shipment, you can look that up. If somebody wants to know, can I get this delivery made by such and such day, you can tell them with a fair degree of certainty, yes, we can, or no, we can't. And that's, important. Second thing, virtual machines, right? So virtual machines, virtual in this context means some computerized version of something like a virtual server or virtual reality, right? And a machine just means a computer. So basically what we're talking about is some construct that does the same work as the original thing. For example, a virtual server is a bunch of computerized things that do the work equivalent to a server, but it's not actually a single physical standalone server machine, right? So virtual machine is the equivalent of a computer, and it could include deployment on multiple instances of hardware, right? So those server functions could be a small part of modules running on many different servers. Software itself could be broken up, again, could be running on multiple different machines, okay? And cloud systems are built around these virtual machines, right? One of the things we talked about with cloud, the users don't generally need to know specifically what machine their data is stored on. They need to know a path to get to whatever machine their data is stored on, but they don't need to know that it's stored on machine A, machine B, machine C. Doesn't matter, as long as the cloud remembers how to connect them to it. And importantly, because clouds use virtual machines, they have the flexibility to assign and reassign resources whenever and wherever they're needed, right? So if one application starts getting busy, the cloud system can generate a bunch of virtual copies of it deployed on various application servers throughout the cloud. And if the need for that application shrinks, guess what? It doesn't need to maintain all those copies. It can, turn some of them off and replace them with other things that people are trying to do. Sorry, I bumped that. Okay. Now our specific example here, migrating supply chain to cloud. Okay, so you have a business, it's trying to migrate all of its supply chain management processes that it's currently running internally under its own roof, and it wants to send them to the cloud. Okay? And the big concern there is that the system can't go offline ever, right? It's not like the business can say, we're going to shut down our supply chain system for a few weeks while we migrate it to the cloud and do all the testing and see how it works, and we're just not going to have supply chain management stuff for a couple weeks. That would basically be shutting down the business for a couple weeks. They're not going to do that. So the big picture migration process, how it's going to work, first two steps. Number one, clone every component from the system, right? Whatever piece of hardware that you're running stuff on, make a copy of that in the cloud, right? Somehow allocate resources for that. Number two, copy the data to the cloud, right? So whatever applications you're running on your roof, whatever data you have, get all those up there to the cloud somewhere in the proper configuration. Once you have that in place, test the component and system functions, right? Make sure everything's working the way it's supposed to. There might be some problems in the cloud that you didn't realize because of the specific configuration you had internally. Those problems only become evident when you decide to break up your application and deploy it on multiple machines. You may find that, oh yeah, the reason why this part of the system ran well enough is because it was all located on one machine. Right? So there are problems like that you might discover. But at some point, we're going to assume you've tested it, it works well enough, and when that cloud-based system works well enough, then you start using it and you shut down the internal system, right? Because you want to have it be up in the cloud. You don't want to manage this thing under your own roof. Okay. Now, specific case of how that might play out. So, supply chain management operations, they do tend to generate lots and lots of data. One bit is transactions, right? So basically, for every handoff of an object at some point in the system, some point in the delivery, there's going to be a transaction there. That's going to be a lot of data right there if you're a large operation. But the real amount of information comes from tracking shipment performance, right? So if you have a lot of trucks run by a lot of different drivers delivering many products on many different routes at many different times of the year and times of day and different weather conditions, you track all of those in a fairly fine-grained way to do it. So an obvious example, you might have one route that works great and is really fast as long as the weather's clear. But if there's rain, if there's snow, it's horrible. Everything grinds to a halt. It's a lot slower. And analyzing that kind of shipment performance is something you would want to do for your supply chain. So anyway, the business has decided to use both BigQuery and Spanner for its supply chain operations in the cloud. So one basic thing you might do as far as workload division, break them up, right? Transactions, that seems like something that's suitable for Spanner, right? Spanner, like we said, is great for doing a lot of small but frequent operations. Like every time you do some update to the database, every time you upload a new data point, for tracking shipping performance, that's something you can do through Spanner. Okay. Other things though, timing and scale of database updates. For example, if you want to run a big analytics project to find out which routes are good, which routes could be better, how you could go about shifting them, that's not probably the sort of thing you want to run through Spanner. If you have these massive database tables, you're probably going to run them on BigQuery. And important, this kind of analysis doesn't need to be in real time. Okay? If you have like a year's worth of analytics data, you can wait like 30 seconds to get the results, right? Other things, transactions, you might want them to process faster. But if you're saying, yeah, we got this big pool of data, we're going to try to find the best route, see what can be changed. Yeah, it's understandable that that's not really going to be a real-time type thing, okay? In particular, it doesn't even really need to be real-time consistent. If you have like an extra 5 minutes or 30 seconds of data that gets included or excluded from your analysis, but you have like a 1-year window of data, that little tiny bit at the end isn't going to throw things off very much. You don't have to worry about that, right? But again, for transaction processing, absolutely need real-time consistency. Just like the ATM example, you don't want transactions to get lost in the shuffle. It's very important that they maintain database integrity. Okay, so that's stuff. I don't know. Do people have questions, concerns, anything you'd like to talk about? Anything you'd like to learn more? All right, then that's all I got. It's been a hoot. Remember, no class on Tuesday, so don't show up here because I won't be here. There will be a remote session. I will announce it through Blackboard. That's it. Enjoy the long weekend. Hello. Okay, I'm listening.
Would there be like a term at the end?
Yes, almost certainly.
Okay.
Yep. You're welcome.
Yeah.